Hello, and welcome to lesson 5 of critical path analysis. We're talking about maximum flow, minimum cut theorem. Okay, so unlike an activity chart, which is what we've been thinking about for this whole topic so far, we're looking at flow diagrams, which represents a transportation network of objects moving from the source to the sink. Okay, so we can see a very simple version of that diagram here. We've got a source, which is labeled S, and a sink, which is labeled T, only because it'd be confusing to name them both S. And it's a directed network. We can tell because there's an arrow there going from the source to the sink. And it also has weights on the edges, which suggests what's called the capacity of that edge. Okay. Now, the context of this could be in terms of traffic through a network of roads, or it could be water through plumbing pipes, or as they're talking about in this particular example, the transfer of data between a network of computers. Okay, so if we have a look at this example here, we've got two computers connected by Ethernet cables of different speeds. The source computer can transfer data to this router at a rate of 1,000 megabits per second. This router can transfer data to the sink computer at a rate of 100 megabits per second. So the question is, what is the maximum flow from source to sink? Okay, well, before we answer that question, I want to show you some work done by another mathematics teacher. His name is Mr. Bodgers. I'll link his channel in the description. And he's made a really good analogy by using the plumbing pipes in his own house. Okay, so basically, you can watch the video, but I'll summarize it here. He shows these two pipes. This is a 3/4 inch pipe and this is a 1/2 inch pipe. He's done some research and roughly concluded, not to a high degree of accuracy, but enough to have a working knowledge to be able to solve these kinds of questions, that a 3/4 inch pipe can take water going through at 89 litres per minute, and the 1/2 inch pipe can take water going through at 53 litres per minute. Okay, so the first question he asks is, what happens if you've got a pump that's pumping water at 70 litres per minute going through both of those pipes? Well, you can imagine that there's not going to be any issue to that speed of water flowing through this higher or this larger diameter pipe. Okay, the 89 litre per minute pipe can comfortably fit 79 litres per minute of water flowing through it. Okay, but if we obviously have a problem in this smaller diameter pipe, its capacity is only 53 litres. So it's going to struggle. In fact, it's not going to be able to send water through that pipe at 70 litres per minute. Okay, so now what happens if we look at this particular situation here, right? If we've got water flowing through this pipe at 89 litres per minute, and then it hits this pipe, which has a capacity of 53 litres per minute, and then after that, it hits this pipe, which has a capacity of 89 litres per minute as well. Okay, so what we can do is we can draw this up as a very simple network diagram. Okay, so we've got our first edge, sorry, we'll do that in blue, which has a capacity of 89. Just check what that, yeah. And then let's say it hits this little junction there, and we'll call that vertex A. Then we've got this edge here, which has a capacity of 53. And that junction there we'll call B. And then we've got our final edge, which will have a capacity of 89 because it's the same diameter pipe as before. Okay, then of course we've got the source, which is where our water comes from, and our sink, which is where our water heads towards. And we'll call that S, and we'll call that T. And finish it that way. Okay, so what we need to understand is that our flow, the actual flow, which refers to what actually happens of water at this point is 89 liters, but it hits that junction and it slows down to 53 here because that's all that this pipe can allow. But what happens after that? Does it then speed up to 89? Well, the answer is no, because this comes after this, and the speed coming through here is 53. The speed coming through there is also only 53. Okay, so the maximum flow, therefore, of this network here is 53. Okay, because that's the flow that goes into the sink vertex at the end. So if we think about this example over here, all right, the maximum flow from source to sink is 100 megabits per second. All right. Okay, and then we have a bit more information, a little bit of a relationship there saying that the flow is at least, the capacity is at least as large as the flow, which is what that means there. And that's demonstrated by this fact. Okay, if these red numbers are all flows and these blue numbers are all capacities, we could see that the the capacity is at least as big as the flow. All right. We've got some more terms here that we'll look at in a separate lesson. The next thing that we'll do is we'll look at what's called a cut. Now you might be thinking, why are we thinking about cutting a network? Well, we'll get to that later as to why we do that. It's a very important reason. It doesn't actually involve cutting any sort of network. There's a much more useful reason to it. Okay, but first things, we'll just look at what's called the cut capacity. Okay, so here we have a network, all right? And what we need to understand is that there are two sides to the cut. Okay. Now a cut can be drawn like that, where you've got a circle, or it can be, if we're talking about this network over here, a cut can just be like that. Okay, where it's just a line that splits the network. Now the important thing is that a cut must separate the source from the sink. Okay. And yeah, and when we're trying to find the cut capacity, we're only adding the edges that are on the source side, okay, that are going from the source to the sink. Okay, so what does that mean? So here we can see, I'll just highlight it here. Obviously, we've got the source side and we've got the sink side of that cut. And we are only adding edges to find that cut capacity by adding the edges that go from the source to the sink, from the blue to the green, okay, from the inside of the circle to the outside of the circle. So we can see this one represents that by the arrow, goes from the source to the sink. The arrow goes from the source to the sink for this one, so we can add that one. And the arrow goes from the source to sink for that one, so we can add that one. So the cut capacity for A, 6 plus 1 plus 7 is going to be 14. Okay, now we're not actually sure what this represents because in the context of this question, it doesn't provide us with one. So we just leave it 14. Okay, same idea over here. Okay, we've got the sink side. All right, and then we've, of course, got the source side here. Okay, so we ask ourselves, with this one, is our cut flowing from the source to the sink? Yes, it is. With this one, so we follow the line of the cut and we can see it also cuts this edge here. Does this go from the source to the sink? No, it doesn't. This goes from the sink to the source, so we don't include that one. And then this cut follows this one here as well. and it goes from the source to sink, so we do include that one there. So we're only looking at the edges that are cut by the cut, okay? And discarding the ones where the direction shows that it's flowing from the sink to the source. So we're adding 100 and 190, and we'll get a cut capacity of 290. All right. Well, we might just leave that there, and we'll continue in the next video.